Okay, so welcome everybody. Happy New Year. Great to be back with a One World Probability seminar. So it's a pleasure to have today Volker Betz and Ben Lees, who will speak about complex spin systems. So Volker, stage is yours.
Okay, yeah, thank you very much. And thanks for giving me the opportunity to present this. So this is a stuff that I did with Benjamin, who is also the speaker. And well, basically, okay, so it's still a little bit in progress, and it's a way to connect spin systems and these graphical models, which is not completely new. But I think it's at least for me, it's now much clearer what goes on, and I just want to share that with you. So it's also have a few questions to people who might be knowledgeable. But so let's start. I don't assume that everybody is familiar with these link models, so I will quickly introduce a little bit about these link models. So the general situation is that we have a graph, and I view a link model as a probability measure, most of the time anyway, on the set of occupation numbers of edges. And in the sense that for each edge, I have an edge and I have a J, which I usually call a color. And I have a number of links of a given color on each edge. So the picture to have in mind for this is that you have a graph. Let's do a simple graph. And then you can put links on the edges, maybe actually two blue links here, a red link here, and maybe three yellow link, actually yellow and an orange link here. So you have different links of different colors that are placed on the edges. And what is usually the case is that you place hardcore restrictions on the types of colors of links that you can place. So the typical restriction is you somehow prevent edges from maybe having too many links or too many different colors. And importantly, in order to make things not, as usually if you don't do anything but that, then things are just independent. But what makes things not independent is that you place conditions on how links meet at vertices. So you can, for example, insist that each vertex must have exactly one link at an edge adjacent to that vertex. So let's say you have a vertex here, and that vertex maybe is only allowed to have less than 5 links, so that vertex would be okay. But if you allow it only maybe 1 link or 2 link, it will not be okay. So you have restrictions on how many vertices links you can place, and that gives you, and this function x, j, and v is going to be the number of links of color j in the occupation number n, so in the link configuration n, that is adjacent to the vertex v. So it's the sum of all edges, so that the vertex is in the edge and of the occupation number. So this is just the setup of a random link system. And the simplest example, which is kind of trivial, is independent edge percolation. So you have just one color. You have an edge either empty or occupied, and each occupation number is p to the number of occupied edges, okay, times 1 minus p to get the usual percolation, but it doesn't really matter. And this always means that if I want a probability measure, I should still normalize it by the correct number. So we are always doing finite graphs here, so there's no problem with these things. So the the picture for this is that you really have your graph here. And independently, you place with probability p a link, or with probability 1 minus p no link. Okay, now the graph is not very interesting, but I mean, you see where this goes. So this is kind of, and I call it percolation in quotation marks because it's of course not percolation, it's just independent edges. I mean, percolation is then a question you can ask about the system, but but this is not really the model. The model is just independent edges. So it's a boring model. So, but a different, less boring model is a dimer model. The dimer model is working like this. You again have a graph. Let's do this graph for the moment. And you have again just one color, and that color you can place. Okay, you can do two things. You can place a link, but the rule is that only one link can be adjacent to each vertex. So you have a link here, you have a link here. You might still be able to place a link here and a link here, but then it's basically that's it. And you might have vertices that have no link. For example, if I do away with this one, there is no link at this vertex here. And when this is the case, they get the factor of beta. And if they have a link, they just get a factor of 1. So the probability measure would be beta to the number, the sum of vertices that have 0 links. And formally, you can set beta to 0. And then this will actually force every vertex to have exactly one link. And this is the dimer model in a general graph. So you just take this, and you already see when beta is 0, this is a relatively rigid model. So in many graphs, you will simply not be able to do it. So whenever you have a graph that has somehow these triangles, it's going to be hard to do it. And so it's a more a combinatorial quantity when beta is 0. But this is another example of a link model. Then the double dimer model is really literally twice the dimer model. So what you get here is, in the same situation, you have two colors, and each each edge can have either one color or the other. So this is what I say here. Each edge can just have either one color or the other. And the rule is that either an edge has to be empty and then it gets factor beta, or it has to be, it has to have one color. And but the other thing is that there have to be, actually in each edge, there has to be exactly one, at each vertex there has to be exactly one edge of each color or none at all. So if I have a red edge here, then I need a green edge at the vertex 2. So I have maybe this. And then I have a red edge again here and here. And I need a green edge again here and here. And I have a red edge again. And then I have some sort of a cycle, a loop running around here. But what I can also do is I can have a green edge here. Oops. Can have a green edge here and a red edge on top of it. So that's allowed because I just allow one link of each color, but I can have two links of different colors. So that's perfectly allowed. So allowed configurations are like this. And now I would have here an empty vertex 2. So that has no neighbor, and that's okay. In this case, another empty one. So that's okay unless beta is 0, and then it's not okay then these configurations are again not allowed, and I'm again stuck with it's more difficult to form these things. So this is the double dimer model, and you see why it's called double dimer model, because if you look at the green, the reds separately, then they form a dimer model. And you just put them on top of each other, and it's a double dimer model. So that's a kind of famous model. And finally, the loop or N model, the final example is one where you it looks almost like the double dimer model. Okay, unless you can have actually more colors, but let's say it's just two colors. That's the loop or two model, and the only difference is that now you don't allow these double edges. So you only have loops. You don't have so this thing here, this double edge, which you have here, that would be not allowed in the loop O2 model. And basically the loop ON model actually can also be phrased. I mean, it varies a bit how you want to do the colors, but it can also be phrased that you have these loops, and the loops have to be monochromatic, and they can't intersect. So you have another loop here, which maybe look like this, and you have another loop here, and they just have to stay away from each other. So they would not share a vertex here, so that would be more place. So these are kind of, again, models of loops. So you have plenty of these models, and an observation with these models is, okay, so first of all, an interesting question in most of these models is about so-called long loops. So you have a huge graph, much bigger than the one I showed you here, and the question is, okay, now you say this is a probability on linked models, and many of these linked models have somehow this notion of connectivity. So you have that two vertices are connected by some loop if you can walk from one to the other by edges of a certain color, right? So then they are connected. Okay, then they may be kind of connected. They will actually, if it's a loop model, they have to be connected backwards. So there's this question of connectivity, and an interesting question is it true that if you take two vertices very, very far apart in the graph, that then there is a reasonable chance that they are still connected by a loop? So in other words, will a random loop model, or in this case a random loop model, will it more look like a collection of very many small loops that actually don't intersect, but they kind of just kind of are very separate? Or will it more look like there's a lot of big loops, and in 3 dimensions they might well be interconnected and go all over the place? So this is the basic question. Are there any large scale structures in these models? Okay, technically what you do, of course, is you take an infinite graph, you exhaust it with finite graphs, and you look whether the probability that you get from one side of the graph to the other basically does not go to zero. However, it's a fact that in many models, a more important quantity, and a quantity which sometimes also is more natural, also when you come from quantum systems, which I won't touch, is not the probability, but it's a funny quotient of two models. So what you often see in many of these models is that you don't ask, is there a probability that you get a long loop, like I tried to indicate in this picture here. But you do the following. You take the partition function, so the sum of all configurations of two different models. One of them has two vertices, and you somehow force a loop into the system and out at the other end. And then you kind of just insist that the model has this open loop, and everything else is up to the model to do. But you insist that this has an open loop from X to Y. And you sum all configurations that are like this, and then you compare to all configurations that don't have the open loop. And this quotient, the question is, does this quotient kind of decay, say, summably in X and Y when X and Y are far apart, or does it decay at all? So is it actually, and it's kind of yeah, okay. It's a question whether it's actually, you can now argue, well, it's kind of almost the same if you have a closed loop, but it's not quite the same, and technically it's certainly not the same. But anyway, so the this is usually the quantity that comes up a lot, and it seems often easier to study for some reasons. And I want now to give you a reason why actually this should be easier to study. So the thing is that this quotient is usually not even a probability, because if you think of the loop O2 model or the double dimer model, then it simply does not have open loops. So this quotient cannot be written as the probability of anything. So it's not actually an object of probability theory at all. It's more like a combinatorial object. And so the question is, where does it come from, and what does it have to do with statistical mechanics? And so to introduce this, I want to talk about complex spin systems, and try to make this as kind of, okay, let's see. So what you should have in mind in all of this is the Ising model. So the Ising model on a graph, I hope, and it's kind of can just take values +1 and -1 on each vertex, and it has a connection. If you have a +1 and a -1 across an edge, then this gives you a penalty, and if you have +1 and +1 across an edge, it kind of gives you a bonus. And the only thing I now change is I don't actually, the Ising model is on +1 and -1, so it's here. +1, -1. And the only thing I do now, actually I should probably do it differently. Sorry about that. I should do it like this. I have -1, +1. And the only thing that I now do is I allow the spin to not only take the values +1 and -1, but to take any value on the complex unit circle. So I have a spin which can take any value on the complex unit circle. And for most of the interesting models, I need to allow a bit more. I have not just one spin on the complex unit circle, but I have capital N spins on the complex unit circle. They all have to be individually on that complex unit circle. And then a spin configuration is that I assign a spin to each vertex and each color. So each color J has a spin on the complex unit circle, and there is an edge interaction configuration. So S is an interaction, and here the S can be in principle any number, but it turns out that the results that are kind of interesting, well, not interesting, but at least some of the results only work if we have non-negative interaction. So even though the spins are complex numbers, the interactions between spins have to be non-negative. And now that should probably be, sorry about that, that should be just real numbers here. So R plus actually, R plus. So I really want them to be non-negative. So okay, so let's see. So I do the usual thing. I say this is kind of my a priori measure on the vertices, and this is my, and I actually allow a measure on the. I don't insist that the interactions are deterministic. So I allow some measure on the interactions. So then what I do is I do the usual statistical mechanics thing. This one should look familiar. So it's the spin at vertex V times the spin at vertex W, like in the Ising model, plus one, and S would be the number one. So it's that would be the usual Ising spin, and this would be, now I have n components, so I have it across an edge. But for one edge, this would be the energy contributed by this particular edge. Then I sum it over all edges, exponentiate it, and that gives me the energy. And since now my interaction is still a measure, I integrate it with respect to the interaction, and I call that thing in kind of like in the usual spin systems, I would call this the Boltzmann factor. So that's just something which assigns a number, actually a complex number, to each spin. And okay, so the complex spin system is just a complex measure on the S to the V. V is the vertex set, S is the spin space, with a Boltzmann factor weight and the product over the single side measures. So here's a product measure, and it's kind of made interesting by introducing this Boltzmann factor. So it's like in the Ising model, and I use the following notation here. So Z is the partition function. It's just what this thing is when I integrate it with respect to the spins. And the Z of F is kind of, if I integrate it with respect to a function. So it's just a number. It's just a way to write it. You could write it with angled brackets or something, but it's the way. And okay, so this is in principle a complex number, but in many cases it's actually a positive number. And if this is the case, I will call it admissible. I will give you a few examples very soon. So for the moment, we just kind of mimic everything that we know from the Ising model. Another thing that we mimic is we introduce a somehow magnetic field. So we have an H. Again, think of n equal 1, then it's just a real number. And I introduce this psi h, which is just exponential of h times the average, actually the sum of all spins. And again, I have to do it with more components, but you think of n equal 1, then it's just the sum over all spins times h. And then this means that I shift somehow the spins in the direction of h. In the Ising model, I would somehow say for h bigger than 0, I would prefer the plus spins. For h less than 0, I would prefer the minus spins. But here it's, of course, a bit more complicated because everything's a complex number. Okay, but if the thing is admissible, then this set is positive at h equals 0. So it's positive in a finite graph, right? Everything's continuous. It's positive in the vicinity of 0. So I can actually do the thing that I always like to do in statistical mechanics. I take the logarithm of that set divided by the number of vertices and get something which I call the free energy. So it's complete, kind of just complete mimicking of what I do. And now the thing in spin systems is always, usually you take this free energy, you take its limit as the graph gets infinite, you look at it as a function of h, you prove that this thing exists as a function of h, and then you look whether this is analytic at h equals 0. This is one way of investigating the Ising model in 2 and more dimensions and find that it has a phase transition. So it's not, in this case, it's not analytic. So this is the usual way to do, and a kind of almost equivalent way up to technicalities is or maybe significant technicalities, but still, is to just do it differently. So you take, instead of first doing the infinite volume limit and then looking at analyticity, you can also say, okay, the point where things will go wrong is h equals 0 anyway. So why don't I just study the second derivatives of this quantity, or any derivatives of this quantity at h equals 0? And if they diverge, then it's probably going to be something terrible. So I just take the finite volume free energy, look at the sequence of, in this case, second derivatives, directional derivatives in some direction h, and look at the sequence of these second directional derivatives. And if they diverge, then this function will probably, second derivatives will kind of look like this. And that means that the function is going to have something like this here. So it's this thing that you would expect. So it's not quite the same as the other order of limits, but okay. And so just to see where this goes, I mean, let's do the first example, the Ising model, which we know well. Here the edge weight is just sitting on beta strictly positive. The vertex weight is concentrated on -1 and 1, as I said. And then you get the Ising model. It's not a complex spin system really, because it's kind of real spin system. But anyway, so this is the Ising model as you know it. And the free energy is exactly this. So it's the logarithm of this quantity. And the second derivative of the free energy, as is well known, is just the sum. It's just the average of the spin-spin correlations, right? And this diverges in 2 or more dimensions if you're in the long-range order regime, and if it's not, it's actually the right thing. So you have the second derivative, it diverges if you have long-range order, and that means you are above the critical point, or kind of below, depending on when you say temperature or inverse temperature, but you're kind of in the long-range order phase, or it does not diverge. So you have this connection between a long-range order and phase transitions. And so for complex spin systems, somehow I claim that this actually leads precisely to these graphical models. And this is how it goes. So the special thing about complex spin systems is that complex measures can very well have a lot of moments equal to 0, right? So real measures, usually second moments are never 0 unless the thing is concentrated at 0. So it's really non-trivial. Real measures, even moments, are not 0 usually. So but for complex measures it can be the case. And now let's link these complex spin systems back to these linked systems. So I use this multi-index notation. So for occupation numbers, I use the n factorial as the product over na factorials, Zn as the product over Za to the Na. And I define the mth moment of a complex measure to be just that. So it's Z to the M. M is the occupation number, gamma dz. So it's really a kind of, okay, it's a full occupation number. So it's a Z1 times M1, Z to the M1, Z2 to the M2, and so on and so forth. So that is the thing. And then I integrate with respect to this. And then I have here I recall that this is just the number of edges of color J that are adjacent to vertex V for the occupation number N. This is what I defined before. And so the bridge between these complex spin systems and the graphical models is that the partition function of them, so it's one bridge, is the sum over all occupation numbers 1 over n factorial product over the n-eth moments of the measure nu e product over the mx nv's moment of the measure mu v. So what you do is you really sum over all. Let me try to draw a picture here. You sum. Let's say you have a just one color in this case. So you have a occupation number that is this, 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 this. So you would have here that is x v is 2, and here is also 2, here is 0. And you multiply all these moments, and you already see that if some of the moments are 0, then you get a 0. So you can get already exclusion rules for this. And okay, then you can also have this product over the edge moments. But for the moment, let's say this is a big 1. So we can focus for the moment on models where the edge measures are just 1. Okay. And so this is a combinatorial formula somehow for the partition function. And okay, there's a proof, but I'm kind of running relatively late already. So the only thing, I mean, you can look at it. I guess you have access to the slides. It's not that difficult. So it's actually a more general thing. So you can actually get a formula that integrates functions that are products of vertex functions and products of edge functions, and you can integrate those functions with respect to this complex spin system measure, and you get a formula that looks similar. It has the 1 over n factorial here, and it has these guys here. And what you do is relatively simple. First, you fix all the z, and you just look at the kind of generalized Boltzmann factor. So this would be the Boltzmann factor without this g, but with the g is again something else. You first write this exponential, which still has components 1 to n as a product of exponentials, and then you just expand. And then the only thing that is kind of noteworthy is you expand this for each k, then you pull this sum through the product, and whenever you pull a sum through a product, you get a sum over occupation numbers. That's somehow the rule. So you have here you pull that sum through the product, you get a sum over occupation numbers. For the moment, only of 1 to n, because you pull it to a product of n factors, so you get occupation numbers here. And then you still have another product. You pull that sum through that product, and that gives you the sum over occupation numbers e times n. So it's as easy as that. So whenever you pull a sum through the product, you get a kind of sum over occupation number of the factors of the product, and that's what it is. So it's not really kind of rocket science. But anyway, the first thing where this works, and it's actually well known, is the random current representation of the Ising model. So this is the formula we had. This is this kind of moment formula. So the moments for the Ising model are just all beta, or actually 1 if beta is 1, and this one is these one are the moments of the +1 -1 measure, and this is a symmetric measure. So the odd moments are all 0, and the even moments, they are all 1. So that means that the combinatorial thing that you get, okay, you get a kind of beta to the number of edges, okay, but then you get just a 0 if there is anywhere an odd number of edges at any vertex. So you have to have even number of edges at the vertex. And so that means that this is the random current model. You have a lot of loops. And okay, so somehow you have no restriction on the number of loops, but this 1 over n factorial saves you because it makes everything finite. If you have too many edges, it kind of get a small number. And but then interestingly, if you look at the z of zv tilde zw tilde, so if you just plug in two spins and integrate that, then the effect is that you already have somebody at this vertex. So you have somebody already at this vertex. So you want still an even number because that's the moment. So you have an odd number here. And somehow by parity of the graph, you can only repair this by having an odd number somewhere else. So you that means that these 2-point functions actually mean that you put a current through your system. And that's the random current representation, basically. So it's a famous representation which helps to do things for the Ising model. And so let's go at the first non-trivial actual random spin systems. So I'm here, again, still n is 1. The edge measure is trivial. And the vertex measure is just the uniform measure on the complex unit circle. So it's here on the complex unit circle, the uniform measure, plus 1 over z. Okay, beta is the monomer activity. So let's, for the simplicity, say that beta is 0 if you want. Or we can also keep it. So we have this measure. And the interesting thing is that there are not many moments that are positive of this measure. So the 0th moment is positive because this is the uniform measure on the circle and just integrate over it. So that is just beta. But then the first moment, so if you multiply this by z, then this gets a 1. So this is positive. But this already is negative because you have z times dz. You integrate this over the unit circle, and that gives you 0 because of the symmetry. And actually, it's the same. Actually, somehow it's the same for z squared. It's also 0. Why? Because it's basically a sine cosine thing, and by the periodicity, this thing is 0, right? You write this as e to the I 2 pi x, and then you have I 4 pi x. You integrate it around, so you see all moments are 0. So that's kind of the key. So by these complex measures, all these moments are 0, except the ones where you kind of have a constant here, and that gives you that well, you can have as many you can have as on the edges you can have as many links as you want, but you must have 1 or 0 at each vertex. So that means you have to have dimers or monomers. And if you do the second derivative, which we say should be linked to the phase transition of the complex spin system, then you see that you already get a factor of z at v. So you get zv times zw, integrate that. And that means that since you already have some, you cannot have any others and you cannot destroy it. So basically it means that these have to be empty and they don't get a factor of beta, they just have to be empty. And then because of this second derivative, because of the logarithm, you divide by z. So you have your ratio of partition functions, the ratio of the thing with two monomers with this without monomers. So there's a monomer called monomer correlation in this model. And if beta is equal to 0, this is not even a probability because there are no monomers in Z in this case. And now, if your graph is translation invariant, then you have a double sum here over V and W. You can replace it by a single sum by translation invariance, and then you get this expression which is just the quotient of something with monomers and without monomers. So that's the monomer. And let's do the next example still. That's the double dimer. The double dimer, especially for beta equals 0, is literally just the product of two dimers. So now you have two colors. You have the edge measure that insists that two colors, and actually that allows two colors. So it's the Dirac measure at 1, 1, and it is the complex measure is just the product of the two. So here's 1 over z1, here's 1 over z1, 1 over z2. And then you look at the moments. Okay, the 0th moment is beta, and the 1, 1 moment is 1. So you have to have a z1 and a z2. Otherwise, you are 0 because you just it's a product measure. So if one factor is 0, that's 0. So that means you have to have somebody of each color intermittently in order to get not 0. So you have the combinatorial pictures that you have actually double dimers. And the loop O1 model is tough because let me give this example still. I'm running out of time much more quickly than I thought. This is possible, right, for the dimer model. And it's possible because I don't place a restriction on the number of links that I put on an edge. It's just I just don't restrict. And there is no way that I can really restrict the number of links because the edge measure has to be non-negative. So if I have something which is not at 0, an atom, it also has to be supported on a non-negative half axis for reasons that I'll at least mention later. And that means all moments are positive. If I'm not kind of at 0, then at least all the moments are positive. And that kind of helps somehow. That's a problem because I cannot prevent these double edges from occurring. Okay, I can do something else. And here I just give you a picture. Let me give you this edge measure. I have an edge measure that looks like this. I have, let's say, 4 colors, and they repeat. So I have here yellow, blue, yellow, blue. I have, this is purple, orange, purple, orange. No, that should be orange. And so I have this thing. And now the way I do it is that each edge can only support exactly one color. It can have as many links of a color as it wants, but only one. And this is by saying that my edge measure is for 2 colors, for example, it would be the sum of 2 Dirac measures. So here, one here, and one here. And that means if you multiply it by, say, S1 times S2 and integrate, then one of them is always 0, and you get a 0. So you have basically, by placing them on the axis, you insist that your weights are actually monochromatic. And that helps because now you can insist that you have at each vertex, and this is what I try to do here, at each vertex you need 2 colors that are not the same matching together. And then as a net result, what you get is loops that kind of cannot backtrack to themselves because they would otherwise they would have 2 then at the same vertex there would be twice the same color, and this is explicitly not allowed here. So that gives you the so-called loop or N model, and it's kind of difficult to get it. I mean, we had to be a bit creative to do it. Okay, so that was the first section, and time is up. I'm kind of a bit shocked, but It's the very first time I talk about this, so I had no idea how long it would take me. So what I'll do is I'll at least give you the basic results of what comes, because the reason why we kind of bother with this, I mean, this is a nice toy, and you can kind of get all these graphical models from complex spin systems, but the actual reason is that for complex spin systems, in a relatively general setting, you can prove reflection positivity. So as I said, I was actually planning to spend some time with this, and it's not going to happen. So, but for those who know anyway what it is, so the thing is that you have to reprove a few things, because you're dealing with complex measures. You have to be a bit careful with positivity. You have to be a bit careful with complex conjugation and all these things. So you have to reprove a few things. But the net outcome is that a complex spin system on the torus, you're always on the torus for reflection positivity, so you kind of ZD times a finite box with periodic boundary conditions. You assume that all the vertex measures are the same. In all the examples we had, they are the same. It has non-negative moments, so that's also, we always had this, and moments are non-negative. And nu is a reflection invariant family of positive measures. And that actually allows this thing, because reflection invariant just means that if I put a reflection plane through here, through an edge, then this has to be the same. So I reflect across this edge, and so it's not translation invariant, but it's reflection invariant because it kind of changes from blue to yellow to blue to yellow. So if I take any reflection plane, then it's going to be somehow the same system if I reflect it across that plane. So here I have a bit more freedom. And so if I have that, and it's very, very important for this thing, I don't think you can do it without, is that these measures are supported on the non-negative quadrant. So there have to be positive edge weights. Otherwise, I don't think it's going to work. So, but then a certain quadratic map has its max. Sorry. So you have a map which has a maximum at u equals 0. So it's a very abstract statement, but it leads. I'll not give you the proof. I mean, you can look it up, but okay, I'm sorry. I just completely underestimated the time I would need to even give the examples. So the thing is that this eventually leads to proofs of long-range order. So what can we do? We can somehow reproduce a proof of Lorenzo Taggi in 2022 and subsequently of Taggi and Quitman for long-range order in 3 and more dimensional double dimer models. That's something we can do with our methods in a kind of, I did it completely in a graphical way, and we can now do it with the complex spin systems. We get reflection positivity and long-range order. So we can prove that in 3 or more dimensions in the double dimer model, which I presented, there are long loops. So that is kind of a direct benefit of these complex spin systems. And the proof of reflection positivity is comparatively simple and general of these complex spin systems. So that's also something which we think is interesting. The problem is that we cannot do the loop or n model. And the funny thing with the loop or n model is that since we have, okay, this is just now for the people who've seen it before, is that for the loop or n model, usually you get something where the Laplace operator, there's a Fourier trick, and there's a Laplace operator on the left-hand side. Let me look for it. It's this one. It's the Laplace u here, Laplace u here. And the thing with these edge weights, which are not always the same, is that you don't really get the Laplace operator. So what you really get is you have this epsilon j of k, which is something like k squared for small k. And this is actually jk squared. This is sum over k jk squared. And you get kind of the something which is very, very close to something which you can use to prove long-range order. But what you would need, and this is kind of a funny thing, just by the fact that you are now dealing with the loop model and not the double dimer model, is you would need to compare two different quantities. So one is the quantity where you just go from 0 to v in any case, and one is the quantity if you go to 0 to v, but you kind of not allowed to use one certain direction. This is because this is why it's kind of so J and L are crossed out. You're not allowed to use the first, say, direction in going out of 0. So this one is a forbidden direction, and this one is a forbidden direction of going into V. And you would have to compare these quantities in some way, in some meaningful way, to the quantities where you're not forbidden to use that edge. So you're just forbidden to use one edge, and you don't think it matters much, because it's especially in high dimensions, you have kind of D is 500, you have 500 dimensions, you're not allowed to use one of them, and you think it doesn't matter. But it's technically you don't know what to do, and it's kind of it's very, very hard. If you could kind of in a good way say that it doesn't matter, you would have log range order, but you can't, and so you don't have it. So we are stuck here. I was going to ask kind of to explain more closely what we had, but it's not going to happen. So sorry. At least I think I gave you the basic model and the examples. So let me wrap up. So the thing, complex spin systems somehow are a bridge between statistical mechanics and graphical models. As I said, they're not completely new. I mean, the random current representation is known, and somehow they also appear in a paper from last year by Lorenzo and Y, and Vaivo, I guess. Yeah. So because we also talked about this a little bit. So somehow they come up here and there, but I think it's worthwhile doing them a bit systematically, because by this moment picture, so what are the moments of this complex measure, you can relatively easily construct all sorts of funny link models which come out of this system. So you have a bridge from complex analysis, also via complex analysis or simple complex analysis, really, from these complex spin systems to graphical models, combinatorial models, and under relatively general conditions, they are reflection positive. And so what we can do is we can extract long-range order if we have uniformly positive edge weights, which kind of really means that certain weighted graph Laplacians can be lower bounded by uniform Laplacians. So the weights is something like a uniform ellipticity condition that we have to have. Then we can extract long-range order, but other than that, we can't. So that's somehow all I had. Sorry for not even telling half of what I wanted to, but anyway, so thanks for listening.
Yeah, thanks, Volker, for a really nice talk. Like, even without telling maybe what you wanted to, like, as you said, it was a very nice introduction. So we have time for maybe some questions for the audience. So as usual, feel free to unmute yourself or raise your hand or put it in the chat.
Maybe can I ask a question about, can you prove the absence of long-range order and long loops in 2 dimensions? There are probably some continuous symmetries that you can use.
That's a good question. I mean, we've been thinking about this actually. So because you haven't, I mean, that was a question which also motivated me a little bit, because you see in these 2-dimensional models, link models, you think of having Mermin-Wagner, but there's no continuous symmetry, right? No obvious continuous symmetry in these link models. I mean, you're on a lattice after all. But of course, once you have these complex spin systems, you somehow have a rotation. I mean, you have a rotational spin. So you could think that there is this continuous symmetry coming up, and there is actually an old proof of Mermin, I don't know actually, but the thing is, the proof of Mermin-Wagner don't really work with complex numbers, if I'm not wrong. So we are not. I mean, it's a very good question and a natural thing to ask, but we have no good answer at the moment. So this is certainly something which I would love to see if somebody could kind of really use this rotational symmetry of spins in a meaningful way. I don't know whether it can be done.
So perhaps the paper of McBrien and Spencer could be useful here.
Yes, but okay. So I guess maybe when you looked a bit more into this, but I think
yeah. So McBrien and Spencer does use these complex rotations, so it's a very natural candidate to try. I don't remember the details, but it doesn't go through in the same way. And other methods are either using, well, at some point Cauchy-Schwarz, which we can't do because of complex measures, or they're using something like the relative entropy, the Kolberg-Liebler divergence, which we don't have also for complex measures. So yeah, McBrien and Spencer is definitely a natural thing to think about, but at least for how much we've tried, it hasn't worked so much. But that's not to say that it can't work. It's just
but
it needs more time.
It's definitely something which I have some hopes for, because in a sense the fact that you have a complex rotation, at least it may actually a rotational symmetry, right? If you just rotate all spins, it's the same. So but it's now we have a complex measure, and some things just don't work so well with complex measures. So we will see. I mean, I have some hopes. Yeah, I think it's a very, very natural and good question.
Yeah. All right. Yeah, maybe with a look at the time, maybe if somebody has a quick question, please feel free. Yeah, Andre.
Yeah. Thanks. Just a very short question. Are you working on C2 or CN? I think at the start you mentioned CN, because in this case, naturally you have additional complications, probably in terms of several complex variables, which would be very interesting to include. But just a question.
Well, in principle, we are actually having a CN, general CN.
Okay.
So far, we don't use a lot of complex analysis. So for us, it's just, I mean, in a sense, we are still using simple-minded things. But yeah, formally, we are actually using high-dimensional powers of the complex numbers. But only the torus, though, right? I mean, we always restrict our spins to have length 1 in each direction. But anyway, yes, many interesting examples actually require n to be larger than 2.
Thanks. In this case, probably you have additional issues here. This is much more difficult, right, in CN?
Possible, but there's also some models that work into. So those things which we did so far, they don't need. Well, you could kind of write them. We choose to write them like this, but you could also just write them with complex exponentials. So e to the I r 2 pi and r is real. So it's kind of a bit of a choice of notation also. We don't do genuine complex analysis yet here, but maybe once you want to do it, I'm just aware that high dimensional complex analysis is not an easy field, but I don't know much more.
Thanks.
Okay. All right. So maybe with a look at the time, thanks again, Volker, for a really nice talk. And let's maybe do like a 2-minute technical break just to change the setup, and then be back in 2 minutes.
Yep.
Yeah. So Ben, you might.
Ben, if you want to start sharing.
Yeah. Actually, I need to be right back.
Okay, I'll be back in 1 minute. No, that's worked.
All right. So, Ben, you're ready? Or
Ready but muted. Okay, good.
okay, looks good. Okay, so yeah, then welcome back to the second part. Speaker is Benjamin Lees. I was going to speak about different types of percolation for graphical models. So, Ben, here you go.
Okay, great. Yeah, thanks for the invitation and Happy New Year to everyone. Hopefully you all enjoyed the Christmas period and it maybe wasn't quite as chaotic as some parts of Northern England were. So this talk is going to focus more on the graphical representation side, or entirely on the graphical representation side, as opposed to the complex spin side, because there's a lot of interesting questions we can ask and some answers, but lots of open things left to be done. So remembering the graphical representations that we saw before, we saw that, okay, some spin systems are real or complex. So the Ising model or this complex spin system on the graph have some discrete models that we build up from links that might have some colors and maybe have some restrictions at vertices and edges that amounts to an interaction between, say, loops or paths and so on. But if our model allows, well, so a lot of the time what we saw actually was hardcore repulsion, so that is an interaction. But if we allow, say, more than one link on the same edge, or if we allow multiple paths or loops to meet at vertices, we need to decide what interaction they will have there. So this could just be something simple like a 1 over n factorial, where n is the number of times a path goes through the vertex, or something that discourages having too much activity at one vertex, or it could be something else. And a lot of examples, the ones I'll mainly focus on, this will come through a vertex weight that depends on just the number of, say, visits or the local time at a vertex, and a pairing function that decides how to join together vertices and associate them to each other at, links, that join together links to decide how to associate them to each other at vertices. Okay, so this is a bit like the example we saw before, except here we have more links. So edges have a number of blue or red links in this case. We have 2 colors. And at each vertex, we're deciding how we want to join them up. So we decided, say, at this middle vertex, there are 3 red links, and we want to join up these 2 links coming out the top, so associate them to each other, and leave the third one on his own. And similarly for other the other vertices. So from this, we get a system, we get some paths. Some of them are closed, so we'll call them loops. And some of them are open of various lengths. So we could have a very small path, open path of just one link, like we have several in the top right. Or they could be a bit longer, like the bottom left, although still only length 2. But in principle, they could be extremely long and perhaps even diverging length. And this is something we're particularly interested in. So our configurations are going to consist of 3 ingredients. The links, N, and their colors, C. So we could either decide to place links and then color them, or decide we want to place all our red links and all our blue links and so on. This is, of course, equivalent up to some multinomial coefficient. And then in addition, we have pi, which is informing what our interaction is. And this is just the way of joining these up at vertices, joining the links up at vertices. And it follows the rule here that if I join up 2 links, they have to have the same color. So the paths are all monochromatic. This could perhaps be relaxed if you wanted. But in this case, not every link has to be paired at a vertex. So in the example above. But in a lot of interesting examples, it might be the case that every single link has to be paired to some other link of the same color at both endpoints. So, for example, this configuration couldn't be allowed in that case because there's no way for the middle vertex to have every red link paired to one other link, right? There's 3, so we will always have 1 left over. And so if we define a local time nx, this is the number of times we're visited by a path. So, for example, the middle and bottom vertex has 2 visits from these blue paths and 2 visits from red paths. It's the same path, but it visits once at the start and once at the end, and hence has local time 4. And for other vertices, we can do similar. Then we can define a measure that takes every vertex and weights the configuration by some function of the local time at that vertex. So this should be a nz, not an nx. But yes, so it's looking at the local time at x. And then in front, we have a beta to however many links we have divided by this number factorial. So this is very reminiscent of what we saw in the first talk. Now, if we have the case where every link has to be paired at each of its endpoints, like I mentioned before, then everything has to be a loop. There's no paths left open because they'll always be paired. So the only thing we have are closed paths, known as loops, and we have a gas of them that interact in some way when they cross themselves or other loops, or where they meet at vertices, or where they cross the same edge, things like that. And a natural question is, like we asked before, will there be long loops? We'll call this loop percolation. And of course, if we're doing this on a finite graph, then we really mean, yes, we have to exhaust some infinite graph, some increasing sequence, and look at the lengths of loops and see if the length of the longest loop, for example, diverges as we take this limit. But there's another underlying percolation type thing going on here, a more sort of familiar or classical percolation model, perhaps. So the links themselves are like a dependent percolation model. We could say we have a percolation model such that an edge is open if it carries at least 1 link, and if it carries no link, then it's closed. And then the loops live on top of this percolation, which itself is a very dependent percolation, depending on the vertex weight function u, and so is perhaps very difficult to analyze, but we can still ask the question, even if we can't necessarily answer it. Does this percolation or is there percolation here? Do we have an infinite component? And this we'll call link percolation. So if beta is very small, for example, and we go back, and uz, the vertex weight, is not too unreasonable, say it's decreasing in the local time, then for beta very small, there won't be link percolation because it gets very hard to place links. And hence there can't be loop percolation because the loops live on top of the link structure. But perhaps there could be link percolation without loop percolation. So we have infinite components of edges that carry at least 1 link, but they all contain just very small loops that are sort of broken up as we go, and there's no way to trace a single long loop through this infinite link cluster. It turns out to be very hard to answer this question, and depending on when I have time or not, I'll return to this model later. But for now, I want to introduce a very nice model, very nice probabilistically, and also has motivations in statistical mechanics that makes it attractive for study, and where there are some answers, some very nice answers, in fact, but also many, many more questions. So the model is random transpositions, and so it works as follows. Let me take a graph. In this case, so I just have a line of 7 vertices. These grey lines connecting the vertices we think of as the edges of an underlying graph. And then we attach a Poisson-point process to every edge independently and run it over time beta. And the events of this Poisson process are going to be transpositions that exchange the endpoints, the end vertices of this this edge. So we can draw this as crosses here. And so say on the edge 1, 2, we see that up here near the top, there's a transposition that exchanges the vertices 1, 2. And in this way, we build up a random permutation that's built from random transpositions. And so this has a link structure, links just being transpositions. So we can think of the connected component of edges that have at least one transposition on them. But it also has a cycle structure or a loop structure. I'll refer to cycles and loops interchangeably here. And so we can ask the same question. Do we have long cycles in this model or not? And can it be the case that we have infinite components of links, but still no long loops? Okay, and well, some original motivation from this model comes from quantum systems, which I'm not going to introduce or dwell on too much, but just to say that we can get interesting connections to quantum systems if we let L be the number of cycles in this random permutation, L for loops. As I said, I'll refer to cycles and loops basically interchangeably. And for some positive, or strictly positive constant theta, we'll take the measure, which is the underlying Poisson-point process of independent transpositions for each edge, but we'll tilt it by a factor of theta to the number of loops. So for example, if theta is very, very large, every time we have an extra loop, we get a whole extra factor of theta. So it seems like it would be very attractive, say a priori, or perhaps naively speaking, to have a lot of small loops and pick up many factors of theta, and that this would contribute the most to the measure. But perhaps this is the case or not. Perhaps it is the case that we have very long loops in this system. And it turns out in some cases we can give answers to this. Although in the case strictly corresponding to the quantum system, we can't quite do this. And I'll mention why very briefly in a minute. But systems of this type, we do expect that in some cases there are only short loops, and in some cases there are long loops. So, okay, and the in a minute has come around already. For theta equals 2, this corresponds to the quantum ferromagnet in the sense that the partition function, or the normalizing constant here, is the partition function of the quantum ferromagnet. And we can also get spin-spin correlations from the loop model. It's essentially the probability up to a constant, the probability that 2 points are in the same cycle, gives a spin-spin correlation. And showing that doesn't decay is basically the holy grail of statistical mechanics, or at least one of them. And so we can't answer this question, although we expect the answer is that there are long loops and there is a phase transition in the quantum ferromagnet, which encourages to go forward. But in some related models, we really can prove that there are long loops. So we're not completely barking up the wrong tree in asking this question. So again, to reiterate the question, we have a dependent percolation of links, these transpositions, and we can ask whether that percolates. And sitting on top of these clusters of edges that have at least one transposition, we have cycles or loops, and we can ask whether there's long loops. And note that, well, for theta equals 1, the edges carrying at least one link is just a Bernoulli percolation, and its parameter is 1 minus e to the minus beta. So in that case, the link percolation is fairly simple to analyze, but the loop percolation is highly dependent on it. And it's a very difficult question. And for theta not equal to 1, it becomes extremely difficult. And we really struggle to say much at all. One thing we can say is that, well, if beta's small, like before, there'll be no link percolation and hence no loop percolation. There can't be loop percolation because it lives on top of the link clusters. But in some circumstances, for example, at least dimension 3 and beta large, we do expect infinite loops. Now, this is a really hard question, but there's some very impressive results. So last year, there was a result that showed that for theta equals 1, there are infinite cycles in dimension at least 5. So this comes from coupling to a Brownian motion and showing that if a loop gets stuck in its past by revisiting parts of vertices it's already visited, it can still escape quite quickly, and hence we'll have infinite cycles. But that's essentially, for this case, the only positive result. But one thing that gives us a lot of hope is that there's a closely related loop model that includes crosses, but it needs an extra type of event for the Poisson process, where there are long loops, at least, and for theta not equal to 1, so even better in this seemingly very difficult dependent case, there are long loops for any theta, integer theta, at least 2. So we take heart from this that we're not completely wasting our time, or at least we take heart from this that the results should be true, there should be long loops. Maybe we're still wasting our time because it's just too hard a problem to deal with, but okay, that's our time to waste, I suppose, if you want to think of it that way. So we'll stick to the case theta equals 1, where we are slightly more optimistic or less pessimistic that we can do things, and ask the question, are there intermediate betas where we have link percolation but no loop percolation? Well, there's some positive and negative. Well, there's some definite answers. The first one is a negative answer. If we're on the complete graph with theta equals 1, the answer is no. So let me take the complete graph, and I'll take my Poisson process on the time interval like beta over n. So beta over n minus 1, just to have the right number of neighbors. And then if I look at the biggest component for my permutation, or my collection of transpositions, the biggest connected component of links, Vm beta, this is like the biggest component in an Erdős-Renyi random graph. And for each vertex in this component, I can look at Cx, the cycle containing point x at time 0, and I can consider the collection of all Cx on this giant component. And in general, there's going to be many of them. In principle, there might only be one giant loop that explores this whole infinite component. But actually, we know that's not the case. And we know even more, thanks to a really remarkable result of Schramm, which is if we take the list of these cycles Cx, we normalize them by the size of the giant component that they live on and put them into decreasing order, then as n goes to infinity, the law of this list, which is a partition of the interval 0, 1, converges to a Poisson-Dirichlet 1 distribution. So not only do we know that there are infinite loops, we know that there's a lot of them, infinitely many of them, and we even know what the law governing their relative sizes are. In particular, this shows that loop and link percolation coincide on the complete graph in this precise sense. And this is probably true for all graphs where the degree diverges at every vertex. And actually quite a bit is known. So it's known that on the complete graph, loop and link percolation will coincide. Actually, so this is known even with theta. It's also known for the Hamming graph. And for the hypercube with theta equals 1, which is also a very interesting case, it's known that loop and link percolation coincide. There are loops of diverging length. So this is strong evidence, I would say, for this claim that probably all graphs of diverging degree have loop and link percolation coinciding. Although I guess we're not too close to a general proof. But okay, it wouldn't be a very interesting question if the answer to it was always no. And it turns out that if we're on a graph of uniformly bounded degree, then the answer is yes. So suppose we're on a graph where the degrees are all bounded above by some d, or say capital D, not necessarily the dimension. So, but for ZD, this would be 2 times the dimension. Then loop and link percolation don't coincide. So this is a result of Morwacher from a few years ago. And there, yes, he showed that if we have an infinite graph, uniformly bounded degrees, then the critical parameter for the link percolation, beta link, differs from the one for loops, so B to C, always. So, well, always assuming that beta link is non-trivial, at least. Okay, in some cases, like Z1, for example, beta link is infinity, but in all the interesting cases, they do differ. In fact, it's even possible to give an explicit bound on the length of this integral. The bound will depend on the graph in a potentially complicated way, but essentially depending on it through the bound on the degrees of vertices. And how is this done? Well, I can give you an idea of the proof because it's a very nice idea and it's also a simple one. And that is that some links can have a link, some edges can have a link structure that blocks loops from traveling through them. So if we look at this structure here, we have two transpositions in a row on this edge, and this red shaded region means that in this region there are no other transpositions. So there's no transposition in these times between either of these vertices and one of its other neighbors. So here, two crosses in a row, no crosses in the red shaded area. So these events essentially block the loops, because if we think of coming in to this vertex from, okay, somewhere else over on the right or below, depending on higher dimensions, then we'll follow this path upwards to find the cycle. We'll cross this transposition, and there's no other transpositions here, so we'll carry on all the way until we get to the second transposition and are sent back. And then, okay, we've got cyclic time, so then we'll head back the way we came, and the loop's been turned around. It's been blocked from continuing. So this leads to an effective decrease. It's like thinning the underlying link percolation, so it decreases the effective beta. And this is basically all we need for the proof. Once we've got our handle on several details. But the idea is this, it's a very simple and very nice thing. So this works nicely because, as I said, if theta's 1, then an edge carries at least one link with probability 1 minus e to the minus beta. So link percolation is just a Bernoulli percolation. But if theta's not 1, then these things become very dependent, and it makes this very difficult. But there are some special cases where we can say a bit more. So trees are a special case, and we can relax this uniform bound into a global condition. So this is an upcoming paper. So take T to be a tree, then the critical parameter for loops and links differ just if the branching number is strictly between 1 and infinity. If the branching number is less than or equal to 1, then think of a Galton-Watson tree. It always dies out. There is no percolation of either type. And if the branching is infinity, then you essentially have enough room to instantly percolate on links. Well, that's Bernoulli percolation, that's okay. And all the room you need to instantly percolate as a loop. So to prove this, we're using essentially the same idea from before, and we're using a bit of theory of harmonic analysis on trees. But just to comment here, I think it's nice and slightly surprising. We were pleasantly surprised that we just need this global condition on the branching number and no further regularity. You wouldn't expect such a simple condition to be true on general graphs. So yes, the core idea is essentially the same. But nicely here, because we're considering, for example, starting at the root of the tree. I've got to do this right. I always draw trees growing downwards, which is obviously nonsense. We start at the root of the tree and we follow it up. Maybe I should draw trees going sideways and just sidestep this problem. So we start at the root, we follow the cycle going along the tree, and all we need is that when we get to a certain vertex, there's a blocking structure if this loop is then turned back at this edge or this vertex and has to try and carry on to infinity through some other path. So that means that our blocking events now only depend on what's happening around a single vertex, rather than in the general graph case where it depends on what's happening around two vertices. And means that we can couple the blocking events to a blocking percolation on odd vertices, and that they're all nicely independent. And then, like I say, we can go through some nice theory on trees that will give us the result. So one of the ingredients we need is, because we don't necessarily have, well, we don't have locally or uniformly bounded degrees, we just have finite branching number. We need to know that we encounter vertices whose degree isn't too high relatively often, or at least often enough. And the reason for this is because the probability of being blocking depends on the degree. It's actually decreasing in the degree. So to prove this, if we consider a random walk on the tree, we'll start it at 0. So this is a random walk on the tree. It's not taking notice of the link structure or the loop structure. It's just an independent random walk just on the underlying graph. Then there'll be some n strictly positive, probably or almost certainly very large, or potentially very large, such that a positive proportion of all the vertices that the walk encounters have degree no bigger than m. This, may seem fairly clear. The proof is not too bad, but needs a very, very nice result to get it. Well, we can see that if that's not the case, the speed of the walk must be 1. But there's this great result from 2002 that gives this bound on the speed of the walk, s, in terms of the branching number, and we can see that the only way the speed can be 1 is if the branching is infinity. So we will encounter vertices, or a positive proportion of vertices with degree less than some, perhaps arbitrarily high, but fixed n. And that will mean that any ray in the tree has to encounter infinitely many vertices whose degrees are at most n, and so each time we have a chance to be blocking, and we cannot get to infinity through the tree. So also simple, a simple adaptation of the case for uniform bound, although interestingly, it's a just general condition, just the branching number, and it depends, or at least our proof is depending on some very non-trivial results that thankfully we already have. So yeah, thank you to the previous hard work that has gone into this field. So an even more special case is a special case of trees, and it's worth saying something about regular trees because there's a lot of nice work here. So in fact, in the model with theta, so with highly dependent links, there is even an expansion of the critical temperature. So here it is to order 1/d². So what is proven in these papers is actually more general. The Poisson process not only has crosses, but a different type of event. And there they get to second order in the relative intensities of these two. So it's more general than this. But in the case of crosses, it reduces to this expression. So we know what the critical beta should look like. And there's even a way to prove that there's a sharp local phase transition for any d greater than or equal to 3. And in fact, we can get an expansion for the critical beta in terms of some alpha k's that we can compute recursively and get upper and lower bounds for any d greater than or equal to 3. So not just an asymptotic statement, but a little bit more, albeit with a inaccuracy of order 1 higher in 1/d. This heavily uses the tree structure, and it seems there's very little hope of getting this to work for any other case, which is a shame, but okay, we shouldn't look a gift horse in the mouth. There's some very nice results for trees, and we can be happy they're there, even if it doesn't give us everything we ever wanted. It's worth mentioning that, as I said, there's lots more nice works on trees, so it's worth looking at these papers and the references in them, but in particular, this started essentially with a work of Angel in 2003, and there's other work, several papers by Hammond, so Hammond and Hegther, although I'm not 100% sure of pronunciation of that name, in 2019 that is also very nice, and many more. But I'm doing reasonably for time, so I shouldn't have to skim too much, maybe not at all. So let's return to the previous path model, where we can't say as much, but maybe we're bolstered with a bit of confidence from the fact that this this previous model of transpositions that seems qualitatively at least somewhat similar has lots of nice results. Yeah, maybe we're more optimistic now. So recall, here's a bigger example of the loop model. It's made up of 3 ingredients. So n, the number of links on each edge. So here, I can even zoom. This is the wonder of having a Zoom talk. So this edge has 2 links. Both of them are blue. This edge has a blue and red link. But perhaps here the blue and green link is a bit better if there's anyone colorblind in the audience. So they can potentially have multiple links. Here they have at most 2, but that's just to do with the resolution of the picture I produced. It could be much more, but after a while it becomes indistinguishable to the human eye, or at least my eye. So we have multiple links. We have some C that gives them a color, and we have some way of pairing them at each vertex in such a way that if 2 links are paired, they have the same color. So here we can see, for example, this edge has 4 incoming links, 1 on each edge, and they're paired up so that the loop does this. From going up into the vertex, it turns right, and so on. And then when it comes down into the vertex here, it turns, well, it also turns right, but on your screen, it's moving towards the left. And so on at the other vertices. So the way the picture is drawn should make it clear what is paired to what. So we have this. It's not quite the case we saw in the previous talk. There we had these more hardcore examples where we could only have either 2 links at one edge, at one vertex, or perhaps only 1 link on each edge, even more strict. But in general, it can be something much more messy than that. So yeah, remember our measure for the 3 ingredients. We can get models that we've seen before, dimers, double dimers, spatial random permutations, ON loops. The most important case is ON spins. So this is like the Ising model, except instead of spins taking values on plus or minus 1, they take values on a unit sphere in higher dimension. So here, a real unit sphere we think of, not a complex unit sphere. But so somewhat similar in spirit to the previous talk, but here everything's real and we can avoid some of the difficulties that come with complex analysis. So our measure, as we recall, was this. We have some normalization. We have something that looks like a Poisson density of links on each edge. And then we have some vertex weight that's telling us perhaps what we should and should not allow at vertices. And if we allow things, how much do we want to reward or punish them? And just as a concrete example, I zoomed out. Yeah, just as a concrete example, if we take the following choice of UX, we get the spin ON model. So UX is some function involving the gamma function of the local time at X, together with the indicator that all links are paired at X. So remember I said if all links are paired, the only things we have are loops. There's no open paths. So we have a system of loops. And if we wanted to talk about spin correlations, as we saw in the previous talk, the interesting case there is where we have loops, but also force an open path through the system between X and Y. So yeah, under this measure, Z is the normalizing constant, total weight of configurations of only loops, and we expect loop percolation to occur for large beta. So compare this to the famous work of Froelich, Simon, and Spencer. They showed long-range order for the ON spins, which is technically corresponding to the case where there's where paths between X and Y can be very large. But okay, let us think of this as loop percolation for our purposes and not dwell on the technical differences between those two. This gives us hope that there's long loops and that we still don't want to give up on looking at the different types of percolation. So in this model, we have an analogous blocking structure, which I'm going to call sausages. So this was named by Andreas Klippel, who's my co-author on this, along with Volker Betz. And I really like the name, so it stuck. So the idea is that this edge has some number of links, but all the links on this edge are paired to another link on the same edge at both endpoints. So any loop that wants to come through here from X to Y can't, because every link here that it might use to cross the edge is already has all the friends it can, and can't let the loop through. So here's the basic blocking structure, but of course it could be more general. We might have multiple links all paired together. or paired together in some more complicated way. But the name sausages should be clear. It looks like either some collection of sausages or some collection of links of sausages. And these will stop loops from going through. So we can use these sausages to show that loop and link percolation differ, but we will require, somewhat annoyingly, that, or currently require, that a kind of FKG condition is satisfied, which in particular we don't have for ON loops. So it's a bit annoying, to be honest. If it's true for the ON spin case, if it's true for the ON spin case, which I'm not 100% convinced it is, then we don't have a proof for it anyway. And it seems very difficult in general to prove. Although, as we'll see in a bit, perhaps what we need is a little bit weaker. Well, it's not clear if it's actually weaker or whether it just appears to be weaker. So the main difficulty, of course, is that everything's highly dependent. It's somewhat analogous to the theta not equal to 1 case for random transpositions. But luckily, there's a lot of work on Bernoulli percolation and lots of nice methods, and so we can try and take some of them. And of course, if we're talking about nice techniques from Bernoulli percolation, some names crop up all the time. And we want to take inspiration from a very nice result, or a very nice method of Domino, Copan, and Tassian, who did this for Bernoulli percolation and the Ising model, but they also have a very nice summary for just the Bernoulli percolation case, which, I recommend looking at. It's only a few pages and very, very nice. We'll get to what they do as we go, as we try and imitate it. So suppose we have a set of vertices V, and delta V is its edge boundary. Then we can look at something like the expected number of escape edges for loops and for link clusters. So first for loops, we'll look at every edge leaving the set S, and we'll consider the probability under our measure mu, where I suppress the beta and n and g and so on, of the event that there is a loop living entirely inside S, i.e. not visiting any vertex not in S, at least on its way from 0 to X. After that, it might leave, but it has a branch strictly inside S that connects 0, the origin, and X. And we'll condition on the event that this edge is open but non-blocking. So open but non-blocking means there are a loop longer than just something happening on a single edge on XY. And in theory, it might be part of this loop that goes from the origin to X, or it might be something else, but this seems like the right sort of thing to condition on. Okay, so naturally, this requires that it's possible to have blocking or non-blocking edges. So if we're looking at blocking edges, ON loops are out, because we can only have one link per edge. But okay, that's good. We can see that for ON loops, the link and loop clusters are exactly the same thing, because we only have one link per edge. And so these two percolations can never differ. Okay, and we have a corresponding thing for links. So again, we look at the edges escaping S, and we look at this not shifted enough to the right S. So this means that just looking at the link cluster, so edges carrying at least one link, that 0 and X are in the same cluster and connected inside S. Given that, the edge XY is open, so carries at least one link, but otherwise we don't specify. So these guys have their own corresponding critical betas. So Domino, Copan, and Tassian defined something similar for percolation. There they only had one type of phi. But so it was a corresponding or analogous definition, just without the conditioning, and they have their own critical beta. So this is completely analogous to this. So the critical beta for link and loop, respectively, are, we're going to look at finite S contained in our set and consider the case where no matter what finite S we take, the expected number of escape edges is strictly less than 1, and take a supremum in beta over this. So the critical beta tilde corresponds, if we have some continuity in the system, to the case where some finite set has exactly one expected escape edge. So it was shown in the case of Bernoulli percolation that the critical parameter for their corresponding phi is equal to the critical parameter for infinite components, the usual critical parameter for Bernoulli percolation PC. So that's what we want to try and do in some sense. What we can show is that below these beta tildes, the connections decay exponentially. So suppose we're on ZD for D at least 2 to be concrete, and we'll take a box of side length n centered at the origin. Then below this tilde loop critical value, the probability of a loop reaching from 0 to outside the box decays like the side length of the box, which hence shows that the beta tilde loop is no bigger than the usual beta critical for loops. Below the beta tilde link, we have exponential decay of the clusters for links connecting in the side length of the box. In particular, this shows that beta tilde link is no bigger than beta link. The proof follows along roughly the same lines as the proof for the Bernoulli case. There's some necessary adaptations, but in this model of links, we do have a spatial Markov property. So if we condition on what's happening all the way along a boundary of some set separating the origin from outside, then we have independence inside and outside. And that is almost everything you need for the Bernoulli case. And it turns out that this is enough for us to get this proof. So this is nice, but we don't know anything about, in theory, we don't know anything about what the beta tilde loop and link are. Well, except that they're no bigger than their corresponding critical values, but that's kind of automatic. So a calculation that we omit, for time, it's a good job I did, will show us that the critical beta tilde for loops is bigger than the critical beta tilde for links. Here we need various mappings that, for example, make a blocking edge empty by tearing the sausages out of the system, or make a blocking edge open by, I don't know, taking the sausage and opening it up into a little loop around the box of length 4 or something like this. So we need to be able to manipulate the configuration at a local level. And this in particular rules out, for example, double dimers. So we really have to be in the case where, well, fortunately, because it's the only case where the result can be true, we really have to be in the case where link and loop clusters are not the same thing, where multiple loops can live on the same link cluster. But okay, we omit that calculation, but it's fairly straightforward. Let me just look at this FKG condition I sort of teased earlier. So it'd be sufficient for us to show that beta tilde link was at least as big as beta link. That will give us the right collection of inequalities to show what we wanted. For Bernoulli, this is usually done with Rousseau's formula, which involves derivatives of probabilities. And well, so as a start, let's just look at what derivatives of probabilities are and see if it's any help. So if we take the probability that the origin connects or escapes a box of side length n along the link cluster, then its derivative is given by this. So something involving the event itself and the total number of links. So here, of course, we should be on a finite graph that we're going to take an exhaustion of some infinite graph, otherwise this is infinite. But okay, we can see that this looks like an FKG condition, right? Well, okay, sorry, this being non-negative is like an FKG condition, and this will be enough for what we need. So we don't have this for the Owen loop case, or at least we can't prove it, which is a bit frustrating. But on the other hand, perhaps this is a little bit weaker, but still true. But anyway, we're not really sure. So as a last little couple of slides, let me look at a discretization of this model, because Rousseau's formula normally doesn't look like this. It looks like something involving pivotal edges. And here we see no pivotal edges. But we can recover something like that if we discretize the model. So here's what I said before, positivity would be enough. But what we want to do instead is discretize our graph. So we'll split our vertex up. So our vertex with time interval beta, we'll split the time interval beta up into a lot of equal length pieces, and then use a binomial limit to recover the Poisson density, the beta to the m over n factorial that we saw. So each vertex will now be n capital M different vertices. And edges will be edges of the original graph together with the same time interval. So we essentially split our naught beta up into a lot of horizontal edges. And to each edge, we'll attach a Bernoulli with success probability beta over n. And the success will interpret as having a link in that little discrete edge that we now have. And so our measure is going to be a measure on now just a Bernoulli percolation on 0, 1 for each of these discretized edges. Is going to look like this. Okay, this is what we had before. We have the edge weights that we had earlier, and we also have this binomial term, and we know that in the right limits, this will converge to a Poisson. Well, now we can differentiate this and see what we get, because we have something that looks like a normal Bernoulli percolation, albeit on a slightly strange graph. And if we do that for A being our event from before, then we do get something involving pivotal edges. So we get a term like this. There's a 1 over m term. Well, okay, if we send m to infinity, this looks like it might disappear. But notice that we're summing over the discretized edges. So this is of order the number of edges in our original graph. So this is like the expected number of pivotal edges on the event A complement. And then we have something else that looks like something that FKG would allow us to deal with automatically, albeit perhaps a little bit weaker than FKG. And so what Doubanil, Copan, and Tachyon do is they don't have this term because they're on Bernoulli percolation, but from this term they extract their phi tilde. They extract phi tilde and the probability of A, and then they have a differential inequality that they can solve, and this very nice method gives them what they need. Well, we can extract a phi link from this term with something like the probability of A left over. Well, the probability of A complement left over. But we don't know what happens with this last term. If we pick our model with U, so that the vertex weight U, so that this is non-negative, or at least uniformly bounded below, then we're essentially done, right? Then we can do everything we want. But we don't know if that's true in some particularly interesting cases. In fact, in the most interesting cases, we don't know it's true. We can always pick U where it does hold, but what we really want is spin ON, because that would be very nice. So the question is, because we don't need FKG in full generality, we only need something about events of this form, and we don't need non-negativity. We just need that this is uniform. This sum is uniformly bounded below, or this whole term, in fact, is uniformly bounded below in N, the size of the box, and in G, if we're taking some exhaustion of an infinite graph. Can we prove something like this? So this is where we are not quite sure. And so one question is that would just be nice as a start. Is this really weaker than FKG? Does anyone know of any system where we don't have positivity of this, but perhaps we have a uniform lower bound? Even that would be quite interesting. We don't know of any systems. But now I'm out of time. I've just pushed the 50 minutes. So thank you for listening.
Yeah, thanks, Matt, for a really nice talk. So we have time for questions. So again, feel free to unmute yourself if you have a question. Otherwise, maybe I can start. So going back to the result like you had before in terms of like the critical values for link and loop percolation on the trees. So you were saying it's somewhat real. It's somehow not something you can generalize. So in particular, like non-amenable graphs are not something you can somehow access, or what is somehow limiting you?
So
you really need to go to
we can take weak limits. Perhaps if Christian is still in the audience, he has some ideas here. It's things we've discussed, and we think, yeah, sure, this method can be generalized to the case where we don't have trees. But I don't think it's going to be the case that we have such a simple one global condition that deals with everything. I mean, sort of how could it be, right? In some sense, it's a silly thing for me to even suggest, right? Give me any graph that's not a tree and give me one condition that this graph has to satisfy for this to be true. Okay, it seems wildly too optimistic. So I don't think anything quite that nice could work or does work. But certainly, yeah, in the case where we don't have uniformly bounded degrees, I still think we could say we can say something. But then this very nice result in the case of uniformly bounded degrees already exists, and this kind of shows how that will work.
So any more questions?
Perhaps one question, if
Daniel.
I may.
Sure.
So one hope would be to make a comparison between a random cluster and classical spin systems.
Mm-hmm.
That would correspond to taking this loop models connected to spins, but with something like n to the number of loops.
Mm-hmm.
And can you handle, I mean, put some colors on the loops or some factor? I think you were looking at it at some point, but
in this case of trees, for example.
Right.
Or,
so on
anything
trees,
like
yes. Mm-hmm.
So we may be able to handle things where, well, we're in the process of finishing up this paper in the next week or two to meet a deadline of one of our co-authors. So at least in the last couple of weeks, we haven't discussed it, but we think something might be possible. That's the sort of the next thing on our list to look at. But I know that there is work. So in the deregular case with theta, where we can, or where this expansion of beta critical can be done with a theta using this sort of Galton-Watson renewal structure that I didn't mention, that I guess you were aware of. So in that case, yeah, I think something can be done, but in general, still something, but it will necessarily be weaker than anything we can say for theta equals 1. And I think necessarily is sort of implying what we're capable of doing, or at least of understanding. It's I'm not trying to say something about what is actually the exact truth or not, where I guess I'm not really sure what the exact truth would be. So I'm sorry, that was quite a vague answer to say we think we can do a little bit, but I'm not confident enough to give you a precise statement, I guess is the summarized answer.
Thanks.
Any more questions? So doesn't seem to. Oh, Andre. Yeah.
Thanks. It may be a weird question, also, but you mentioned during the talk loops and other things. So is there any connection to SLE in this case? And what would be the scaling? I mean, have you even considered, does it make sense? What would be the scaling limits here? Would they be connected to research on SLE? Maybe a different strand, but nevertheless. Thanks.
Right. Yeah, so the answer is I don't know, but if you look, for example, at, I don't think I have a picture of my talk. Okay, I have a picture we can use our imagination on to slightly alter. So if you imagine the loop ON case, where we can only have one link per edge and only 2 links per vertex, then we have a hardcore sort of self-avoiding system. If we force a loop from, say, the left of the system to the right, then the scaling of this is does seem like it might be an SLE curve. For example, it doesn't cross over itself, and it's a random non-self-intersecting curve. The other loops in the system are pushing it up or down in various ways, but it's not clear sort of how much it fluctuates away from, say, the straight line that we pin it at both ends at. So we're not really sure. I guess a starting point would be just to try and simulate this model and see what we get. Although we haven't done that. It's perhaps a very good question for one of my colleagues at Leeds, Amanda Turner, who knows quite a bit about these systems. So yeah, it's a very good question that we have thought about, but I don't know how we prove an SLE scaling limit or another scaling limit. At least off the top of my head, it would probably take a lot of work.
Thanks.
Yeah, right. So any more questions, comments? So it doesn't seem to be the case. So let's thank both speakers again. And just as a reminder for everybody, we're going to have our next session, which is also going to be the last session of the term, already next week. So yeah, thanks everybody for coming, and yeah.